I'm going to give you an example of an alpha decay. How about radon 222? 88. Yes. Oh no, it's raining. Sonny's baseball game canceled. No, please, no. Radon 222 decays via alpha. You'll often get the hint of what kind of decay it is because over the little chemical reaction arrow, there will be the symbol. And you won't always get that because sometimes you'll have to be guessing what kind of decay it is. And what we need to do then is, as soon as you see that it's an alpha decay, you want to put an alpha particle there. I'll do 4,2 alpha. And so what this means is that you start with this, the nuclear reaction happens, and what's left is a small alpha particle plus what's left, basically. This is supposed to be ever so slightly smaller than this. It's this smaller. 4, 2, this thing comes out of this, and so you have these two things now. Anyway, that's what this is symbolizing. And so what we have to figure out is what's left. That's the whole point of this. The point of these kind of problems is that one of these won't be given to you. And as a starting point, we'll start with ones where you just have to figure out what the product is. Sometimes you'll have to figure out what kind of decay it is. Other times you'll get these two and you'll have to figure out what you started with. But let's just do this one. It's really not that hard because your answer will be another isotope just like these. So there'll be a symbol, a number here, and a number here. And the process that you go through to get there is easy because think of it this way. You start out with this thing that has 222 total protons and neutrons, and you lose this particle that has 4. And so to get the total particles, you just do 222 minus 4. Easy enough because what's left has lost this. And so that, for those of you that are not math.
Plus or equals?
I think it's raining.
Isn't it resulting in a different isotope?
Well, no, this symbol is the resulting in. It's a chemical reaction. So on one side you have what you started with, and this implies a change. And then you have this plus this. So you have two things left over, right? You have the thing that came out of it and the thing that's left. You're looking at me like I have several heads, but hopefully
that'd be cool.
Hopefully it'll be clear because
I'm so curious about this analogy. Okay, so there's a pregnant woman.
Seth has an analogy. Let's listen to Seth's analogy.
So after this reaction, don't film me.
Oh yeah, come on, you're on.
And after this reaction occurs, there's the baby and what's left of the mama.
Ooh, that's very good. Yeah. What's left of the mama is maybe not the best way to put it.
High five, Seth.
Full intact mommy and baby, right? Pregnant lady,
But
baby
she
comes
changed
out.
because she gained weight during pregnancy.
Okay, but
Which
still.
is wrong. She lost weight during pregnancy.
On one side, you have the pregnant mother, and if you put the no longer pregnant mother, the baby, and all that other stuff that comes out on the scale, you have the same mass. Okay. I bet that makes this process look a lot less messy. I never thought of nuclear decay as a non-messy process until then. Anyway, childbirth is a beautiful thing. But there is lots of poop and blood which people are not prepared for.
Let's just cut all of that out.
Okay. Anyway, 222 total particles minus 4 gives you 218, right? And then if we look at the other part, which is the 88 protons that we started with, before it spit 2 out, this alpha particle with 2 protons, that means we lose 2 of those also. So it's 88 minus 2 gives us 86. And so that's what we have here. Well, and all that remains now is to go to the periodic table. Do I have my periodic table? I know I do somewhere. Here it is. Go to the periodic table. You find number 86, excuse me, which is radon. And so that's what it is now. It's no longer radium. It's radon, Rn. Those of you that can't see well through my badly written pen, radon. And so it's a new thing. So it starts out as radium. It gives birth to an alpha particle, and we have radon left over. Radon 218 to be specific. Okay, so there's one alpha decay reaction. Shall we do another, since that one was kind of chaotic? I'm going to leave that here.
That's it.
Go ahead. I wasn't going to use that word.
Mr. Arbach, why don't you smile for the camera?
Okay. Lots of editing for this one.
Lots of editing. Alright, I'm going to leave this one up in case people are still writing, and I'll just do the next one in a different color. Can just make sure that we can. Will you be able to get all of this? Can you see
Yeah,
my
let's
hand?
sit up here.
Okay. We'll do this one in blue.
You have coffee on this table, sir.
Okay, now we got polonium 208. Polonium is 84, I think.
Yeah.
Maybe? Yes? Yes, polonium is number 84. And polonium decays via alpha decay. And so that means we know we'll have an alpha particle. Hey guys, what are you talking about? So vociferously while I'm trying to do this.
Vociferously.
Okay, so again, we know that an alpha particle comes out. Our job is to figure out what's left. And again, again, it'll be some sort of isotope with its own atomic number and its own mass number. And this time, we still subtract a different color. How about orange? 208 minus 4. It's always minus 4 in an alpha decay because you're losing 4 particles. That leaves 204. And then down here, 84 protons minus 2. That leaves 82. And if we look on the periodic table, 82 is lead. Lead.
Can't see it.
Can't see it? Lead. Anyway, take my word for it, people at home. 82 is lead, and that's the answer. So, and we refer to this as lead 204. There's a bunch of different isotopes of lead. Lead 204 is another one. Is one of them. Okay. Make sure you write that down. Take your time. You can stop now.